In this video, I'm going to show you how to do a margin of error analysis for a coefficient in a regression equation. The button for it is down here, so I'll click on it. When I do, a set of instructions appears in the description box for how to use the program, and we'll be inputting information into the input box here. Let me first describe the program to you. The program determines the sample size needed to achieve a desired margin of error for a regression coefficient in a multiple regression. This is important because the focus is not on sample size selection for purposes of achieving reasonable power, but instead it focuses on achieving reasonable precision. It focuses on selecting sample sizes to minimize margin of errors for a statistic rather than sample size selection to ensure you correctly reject the null hypothesis of no effect. I have extended discussions in my book about the importance of minimizing margin of errors. As an example, if a sample correlation of 0.4 has a margin of error of plus or minus 0.35 correlation units, the derived correlation of 0.40 is not a very trustworthy result, despite the fact that it is statistically significant. The scenario is analogous to political polls that we see on television that report large margin of errors for surveys or polls that characterize the percent of people who support a given candidate or a given policy. If the margin of error for a percentage is large, we don't trust the poll results. Large margin of errors give us pause about taking a statistical estimate seriously. In my opinion, social scientists have not given sufficient attention to the concept of margins of errors. In my book, I build a case for reporting them on a routine basis. The current program focuses on margin of errors for regression coefficients in linear regression. Because many standard tests we pursue, such as the independent groups t-test, ANOVA, and ANCOVA, can be executed in multiple regression, the program can do a margin of error analysis for a wide range of statistical contexts. Again, see my book in the resource page for details. In statistics, one way of characterizing a margin of error is as a half-width of a confidence interval. For example, if I am specifying the mean annual income of new assistant professors at major research universities and my sample produces an estimate of $70,000, I might find that the 95% confidence interval for the estimate is $68,000 to $72,000. The width of this interval is 4,000 and the half width is 2,000. I would characterize the mean income as $70,000 plus or minus $2,000. There are other ways of thinking about margin of errors, but that is a topic that is addressed in my book, not in this video. I will use as an example a randomized explanatory trial that seeks to increase weight in adolescents with anorexia as a function of a CBT program, i.e. a cognitive behavioral therapy program. Let's take a look at the linear equation that relates the treatment condition to weight gain. The equation predicts the post-test weight from the treatment condition in three different covariates. The coefficient B1 is the mean difference in the post-test body weight between the treatment and control conditions. It directly tells us how effective the CBT treatment was. If I get, for example, a difference of 10 pounds, what is the margin of error I am willing to tolerate around that estimate? Is a margin of error of 1 pound acceptable? 2 pounds? 9 pounds? What sample size do I need to obtain the margin of error I find acceptable? I'll elaborate on this in a little bit. The value of the margin of error observed in data for any given study will vary from one sample to the next because of sampling error. This means that you cannot be certain that when you conduct your study, you will get the exact margin of error value you planned based on the sample size provided by the current program. For example, if we want a margin of error no greater than 2 pounds, the current program provides you a sample size to use that will ensure you will not exceed this margin of error. However, when you collect your data and calculate your margin of error using that sample size, The margin of error may be somewhat larger or smaller than 2 pounds. The concept of an assurance probability, also called a tolerance, refers to the probability that the margin of error will in fact be no larger than the margin of error you specified in the sample size determination algorithms. The larger the assurance probability, the more likely it is that you will observe the desired margin of error if you use the sample size recommended by the program. A commonly used assurance probability is 0.80, and it is the default for this program. In general, the higher the assurance probability, the more your sample size will need to be increased. The program requires that you enter a presumed population standard deviation for the outcome, as well as a standard deviation for the target predictor in the regression equation. I'll discuss alternative strategies for doing so, but in this case the approach is straightforward. Suppose that based on pilot data, I believe that the standard deviation of the post-test body weight will be 15 pounds. So I'll enter a 15 here under the standard deviation of the outcome. Given that I have equal n in the two treatment conditions, the standard deviation for the treatment condition must be 0.5. So I'm going to enter that here. These represent the two standard deviations that I'm going to use. Another parameter I need to specify is the overall squared multiple correlation for the linear equation. The larger this value, the smaller the sample size I will need to achieve my desired margin of error. One of my covariates is a person's body weight at baseline, which should be fairly highly correlated with their body weight at the post-test. Coupled with the other covariates and some pilot data, I might expect that the overall squared R in the relevant populations will be 0.55. So I'll enter those values here. Yet another parameter I need to specify is the collinearity between the target predictor and the other predictors in the equation. This takes the form of a squared multiple correlation that predicts the target predictor from all the other predictors. Because the value of the target predictor, in this case treatment versus control, is defined based on random assignment, the correlation should be 0 with all the other covariates. I therefore enter a squared correlation of 0 accordingly. There are a total of 4 predictors. Suppose I decide to set my margin of error for the mean weight difference between the treatment and control groups to 2 pounds. I'll enter a 2 here, and I'm ready to execute the program. As one final check, as I review the entries in the box, I can see here I made a mistake by entering a comma 50 rather than a 0.50. So I'll correct that comma. It's always good practice to go back and double check all the entries that you made to ensure they're what you want. I'm going to click on Register Input. That generates the syntax for the program. I'll copy that to the clipboard. I'm going to open up R. I'm going to hit Control V to paste the syntax here, and as the syntax is pasted, it will execute. The commands appear in red and the output appears in blue, and I want to focus on the output at the very end here. As I look at this, in order to have a margin of error for this coefficient of plus or minus 2 pounds, I'll need a total sample size of 425, or about 212 individuals per group. If I'm willing to tolerate a higher margin of error of, say, 3 pounds, then I'll only need a sample size of about 100 per group. The output for the program explores a few different margin of error sizes in addition to the one that you requested. Okay, let's look at another example. I'm going to close out R and go back to the input box. Now in this example, I want to look at the effect of a mediator from among a set of 3 mediators on an outcome. The mediator is an index of self-regulation skills that has a continuous metric and that ranges from 1 to 5, with higher scores indicating greater levels of self-regulation. The CBT program was designed to teach the adolescents self-regulation skills on the assumption that such skills impact weight gain. Let's take a look at the relevant linear equation. The equation predicts post-test body weight from self-regulation and the two other mediators, and then suppose I also have three covariates that I'm controlling for. One of my covariates will be the body weight at baseline, and if I hold it constant, then the coefficient B1 will tell me for every 1 unit that self-regulation increases, how much weight gain is predicted to increase. There are two approaches that researchers use to specifying desired margin of errors in this case. One uses the raw metrics of the target variable, and the other focuses on standardized metrics. I come back to the input value box, and I'm going to clear the entries. For the standardized approach, I'll specify the standard deviation of both the target predictor and the outcome as 1, because standardized scores have a mean of 0 and a standard deviation of 1. So I'm going to put a 1 here and a 1 here. I'm going to go ahead and re-enter the percent confidence interval and the assurance probability. And again, I'm going to have 6 predictors in this case. By entering standard deviations equal to 1, this means that B1 in the equation will map onto a standardized regression coefficient, although technically the analysis is done on covariances and not correlations. The desired margin of error is then expressed as a fraction of the standard deviation of 1. For example, if I specify the desired margin of error as 0.10, then I am saying that I want the margin of error to equal about 1/10 of a standardized metric. The sample size result will generalize to any case where the standard deviations for the variables have been equated through some form of standardization. A common standard for standardized metrics is a margin of error of plus or minus 0.10. But this can be sample size demanding unless the magnitude of the overall R-squared is large. By the strategic use of covariates, however, you often can produce reasonably sized squared multiple correlations, such as using the baseline outcome as a covariate. I discuss this strategy more in my book. Without going into all the particulars, here are the values I'll work with in the program. I'm going to set the collinearity to 0.10 for the mediator. I'm going to set the overall R-squared to 0.50. Again, the two standard deviations are 1. I'm going to have 6 predictors, and the desired margin of error is going to be 0.10. Okay. I'm going to click on Register Input to generate the syntax. I come down and I hit Copy to Clipboard. I open R. I'll hit Control V to paste the syntax. And here's the table that results. In order to achieve a margin of error of plus or minus 0.10 in standardized metrics, I'm going to need a sample size of 248 in this case. If I'm willing to tolerate a margin of error of 0.15, then I will only need a sample size of 123. Suppose instead of a standardized solution, I want to use the raw metrics of the variables involved. Let's go through that example. I'm going to close out R and go up to the input box. Using the raw metric is the second possible approach for specifying a margin of error for a mediator. In this case, I'm going to set the standard deviation of the outcome to 15. I already went through the rationale for that. And based on pilot research, I might find that the standard deviation for the mediator is 1. So I'll go ahead and leave that at 1. Remember, it's on a 5-point scale ranging from 0 to 5. And the regression coefficient is going to tell me for every 1 unit that self-regulation increases, how much the post-test mean weight is predicted to change, holding constant the other variables in the equation. Now I likely will get a coefficient for B1 that has a value like 4, indicating that for every 1 unit self-regulation increases, weight will increase, say, 4 pounds. So I might decide that a margin of error of plus or minus 1 pound for this coefficient is a reasonable goal. I'm going to set the margin of error to 1. I double check all the boxes to make sure everything is what I want. I then click Register Input. I get a new set of syntax. I copy that to the clipboard. I open up R, and I hit Control V to paste the syntax. To achieve a margin of error of 1 pound for this coefficient, I need a sample size of 523. If I'm willing to tolerate slightly larger margin of errors, such as 2 pounds, then my sample size that I need in order to achieve that margin of error is about 150. As a final example, suppose I want to obtain the sample size necessary to have a desired margin of error for a correlation coefficient between two variables. Let me close out R, and we'll go through this example. I come back up to the input box. In this case, I'm going to treat the scenario as a standardized bivariate regression with a single predictor, because the regression coefficient under such circumstances will equal a correlation coefficient. Suppose I'm interested in a correlation of 0.50. Here are the values that I'm going to enter. The overall R squared will be 0.50 squared, or 0.25. I only have one predictor. Because there's only one predictor, it won't be correlated at all with the other predictors because there are no other predictors. So entering collinearity of 0. Because this is a standardized solution, the standard deviation of the predictor will be 1, and the standard deviation of the outcome will be 1. And then let's suppose I want a margin of error of plus or minus 0.10 correlation units. I click on Register Input to generate the syntax. I copy that to the clipboard. I open R. I hit Control V. And here are the results. In order to have a margin of error of 0.10 for a correlation of 0.5, I'll need a sample size of about 315. If I'm willing to tolerate slightly larger margin of errors, then I can get away with smaller sample sizes. Technically, this analysis focuses on a covariance with standardized metrics. It turns out that the margin of error for a correlation coefficient will be asymmetrical, and this needs to be addressed through bootstrapping. I discuss this in my book, but nevertheless, this result will give you a pretty close approximation of the sample size that you need. Okay, in sum, I think it's also important when you do sample size determination to think about margin of errors, and this program can help you do that for a wide range of scenarios. Okay, that's it. Thanks a lot.